If you take away the lack of air and water, the weaker sun, the lower gravity, and the toxic soil, Mars isn't all that bad of a place to live. And there are certainly worse places to live, like, I don't know, Ohio. I'm allowed to say that because I grew up there. But there's been a big push in the past 2 decades to not just go to Mars and visit like we did with the moon 50 years ago, but to stay there, put down roots, establish ourselves, build a colony or a settlement. We've got the Mars Foundation, Occupy Mars, Mars One. All of them propose grand plans to build a human settlement, a city, on the red planet within the next generation. I'm going to give it to you straight. Because if you're watching this show, then I bet you're the kind of person that appreciates a no-nonsense approach. We're not going to Mars anytime soon. I know there are some announcements floating around out there. And at the time of this recording, who knows what the current administration will propose that say we should go to Mars in 2026 or 2029. I can tell you with utmost confidence that the people throwing out those dates aren't doing it because they have a well thought out plan of technological improvement to make those reasonable targets. They're doing it because those are the next open launch windows. That's it. Let's go to Mars in 2026 because that's the next time we can go to Mars. It's like saying, hey everyone, I have a plan. We should all go to Barbados at 7:19 tomorrow morning because that's when the next flight is leaving, not because you've actually developed a plan to go to Barbados or even have the money or a swimsuit. But while we can be pessimistic about the short term, we can still be optimistic about the far future. There is no law of physics that makes a Martian settlement impossible. Sure, it will be perhaps the toughest engineering challenge ever, but it's not impossible. And that's a big difference. So let's dive into what a Martian city might actually look like and how we might be able to build one. But first, we need to talk about how a city on Mars will be completely unlike anything we have on Earth. I'm Paul Sutter, a cosmologist, author, and host, and this is Near Futures. Let's start with the raw numbers. The average temperature on Mars is minus 63 degrees Celsius or negative 80 Fahrenheit. While it can get much warmer than that, up to something approximating room temperature in the low-lying valleys during the summer months, it can also get much colder than that, down to minus 153 Celsius or negative 225 Fahrenheit. Remember, Mars is a planet cold enough to freeze not just water, but also carbon dioxide. So number one, any human settlement is going to have to grapple with extreme, bitter, year-round cold. Even the most remote and extreme places on Earth like the South Pole don't reach temperatures that low. And the South Pole has the advantage of, having air to breathe, which Mars lacks. The air pressure on Mars is less than 1% of the air pressure on Earth at sea level. And what air it does have is mostly carbon dioxide, which is great news if you're a plant. Now, it's not that complicated to build a pressurized vessel to maintain a regular, breathable atmosphere against what is essentially a vacuum. The International Space Station does it all the time, and it's pretty big. And it's also designed to hold no more than a few people at any one time. And it's right there in Earth orbit, making resupply and, if needed, evacuation relatively straightforward, at least as straightforward as anything goes in space. But Mars isn't close. The average distance to Mars is 140 million miles or 225 million kilometers. With chemical rockets, a journey there takes months. Just think about it. Usual crew rotations for the space station are around that same length of time. And the Apollo missions to the moon were much, much shorter. So a typical astronaut's stay at Hotel ISS is roughly equal to just the journey to Mars, not including actually, being there and coming back home. And even then, we have to wait for a launch window to open up when the Earth and Mars are on the same side of the solar system, which happens roughly every 2 years. Sorry, Mark Watney, but rescue is not going to be an option, nor is resupply. If something goes wrong or the settlers run out of some critical component or ingredient, that's it. They're going to have to figure it out on their own. Adding to their daily headaches will be a constant exposure to cosmic rays. This is deadly radiation coming in from deep space, from exploding stars and black holes and whatnot. On Earth, our atmosphere does a wonderful job of absorbing most cosmic rays. But even then, they're able to slip through to the surface. You are struck by a cosmic ray about once every second. And these cosmic rays contribute to somewhere between 1 and 3% of all incidents of cancer on the Earth. Mars has no atmosphere, which means the Martian surface gets a lot of radiation. And just simple metal shielding isn't going to cut it. You can't have a wall and make this happen. That's because a cosmic ray can just strike the metal and create a shower of subatomic particles within the shelter. You need a lot of stuff, rock, water, gas, whatever, between you and the dangerous sky. Speaking of rocks, yeah, they're toxic. And not like social media personality toxic, I mean actually toxic. Poisonous, dangerous to touch, breathe, ingest, or otherwise be around. The soil is full of perchlorates, which is sometimes used as an ingredient in rocket fuel. Any food that's grown on Mars will have to use treated soil, which will use who knows how much water. Oh, yeah, that's right. Water. Yeah, there's water on Mars, but it's almost entirely frozen. There might be some liquid pockets buried deep under the polar ice caps, which isn't anything remotely resembling accessible, so we'll just have to leave those be. The rest of the frozen water is buried underground, which means mining. A lot of digging up dirt, heating it, sorting it, and separating the water. Mining itself is going to be a huge problem for any long-term habitation. On the Earth, we're used to just finding ore veins and taking a whack at it. I mean, I suppose the actual process of mining is more complicated than that, but I've played a lot of Minecraft, so I feel like I understand the basic idea. On Mars, this isn't quite so easy. Without plate tectonics to mix up the crust, we have no idea if there are rich concentrations of metals, which means that anything heavy will have to be shipped in from Earth. And we need to talk about the dust. Martian sand. It's coarse and rough and irritating, and it gets everywhere. No, wait, actually, that's the opposite. It's been blowing around Mars for billions of years, and that constant motion has ground the dust grains down to almost perfectly smooth, almost microscopic bits. And when dust storms kick off, they can literally encircle the entire globe. In 2018, just such a global dust storm killed NASA's Opportunity rover. The storm blocked out the sun for so long that the rover couldn't get enough juice from its solar panels, and it went quiet. Any future settlers will likely need to rely, at least in part, on solar power, which means they will be in a constant fight with the dust starting at day one. Like I said, we're not going to Mars anytime soon, because we haven't solved, any of that. Any of these problems. And we're not going to solve them in just a few years. But that doesn't mean that we can't make progress. Before we get to Mars, we're going to have to practice and develop radical leaps in technology, but also practice. A Mars mission will be utterly unlike anything attempted by humanity. We're talking about a group of settlers, maybe as few as an initial team of 4, traveling over 100 million miles away from home to a literally alien environment, one that is so hostile to life that nothing lives there, and turn it into a home. And they're going to have to do it alone. Besides the enormous technical hurdles of such an undertaking, there's also the human element. We need 4 people to get along for years at a time in a tightly confined, high-stress environment. I mean, let's say you like your coworkers. Maybe even you go out for drinks every other Friday. Now imagine after a hard, stressful day at work, you have to have dinner with them and then sleep next to them. And you can't even step outside because the planet you're on is actively trying to kill you. This very real human problem motivates the design of what are called Mars analogs. These are missions based on the Earth, because we have no other option, usually in some remote or somewhat inhospitable location. And we take a team of people, run them through rigorous psychological compatibility tests, and seal them up for a few months at a time to see how everything goes. And to make these analogs as realistic as possible, we don't just let them sit there and play Xbox all day long. We give them tasks to do, tasks that resemble what they might have to do on a real Mars mission. Go out and explore this area and bring something interesting back. Go fix that leaking valve in the tank outside. Go build that new housing structure. Heck, if you want to radio home, there's going to be a delay of several minutes before mission control will get back to you to mimic the realistic communication delays to Mars. For example, there's the Mars Desert Research Station operated by the Mars Society and situated near Hanksville, Utah. Man, if there's a place on Earth that looks a lot like Mars, it's Hanksville, Utah. Researchers spend rotations of up to a few months at the station. It's so rigorous that when participants want to step outside, they have to put on a bulky and heavy spacesuit. The point of this experiment is to see how well people can work together in Mars-like conditions. And it's also to develop tactics, ideas, workarounds. Working on Mars is not like working on the Earth. The environment is 100% hostile 100% of the time. There are almost no natural resources to take advantage of. Every single task, from maintaining the greenhouse to going on an expedition, is slow, arduous, and dangerous. We need lived experience in that kind of environment with detailed logs of what ideas and solutions worked and which ones didn't work to guide future astronaut crews. Another experiment, SAM, for Space Analog for the Moon and Mars, takes it one step further. Built and run by my good friend Kai Stotz, it's about as close to the real deal as you can get on the Earth. It's a fully sealed environment. To enter, you have to pass through an airlock. When you're inside, you're breathing recycled air and drinking recycled water. Crew rotations last for up to a few months, and they can only bring in new materials through resupply missions. There's even a Mars yard where they can simulate field work both by themselves and with the help of robotic rovers. It's on Earth that we're gaining the valuable experience to go to Mars, exist on Mars, and thrive on Mars. But getting everything ready and going to Mars is only half the battle. The other half is, where on Mars do we do all this? Let's say you're in charge of a Mars mission. Okay, boss, where do we land? The total surface area of Mars is roughly equal to the land area of the Earth. Nobody's ever built a settlement there. Heck, nobody's even gone there. It's free and wild and open territory. Yeah, there might be some legal issues surrounding international laws and outer space treaties, but we'll let the folks back home deal with all that. You're in charge, and you have to pick a spot to plant down roots. Where do we start? Let's assume you packed a sandwich or two for your settlers, which means you have to tackle 3 problems immediately, right off the bat. Access to water, access to good sunlight, and protection from radiation. And this means you're going to have to make some trade-offs. You need water for, well, everything. You need it to irrigate crops, to make coffee, for sanitation, and for fuel. Yes, there's a chemical reaction you can use to combine water with the carbon dioxide in the atmosphere to make methane, which can serve as a rocket propellant if you ever want to leave. And as for energy generation, fossil fuels are not going to be a good idea because no fossils. And while nuclear can be a powerful option, you'll have to navigate 2 major hurdles. 1, the technical challenge of getting a nuclear power plant to Mars, and 2, the political challenge of convincing everyone to let you take a power plant to Mars. Now, I should do a whole video on nuclear power in space, so feel free to ask, and how we're not going to do anything really useful until we solve that. But in the meantime, we're going to have to stick to solar. A lot of it. Mars only gets about 2/3 of the sunlight that the Earth does, so you need a lot more solar panels, and you'll be constantly battling the dust, and you'll want to use that same sunlight not just for energy, but to grow food. And radiation, well, radiation is everywhere. There's no magnetic field and no significant atmosphere. Everywhere you go on the red planet is a danger zone. Your only hope to avoid it is to dig deep. So how do you balance all three? Most of the Martian ice is found far from the equator, where it's colder year-round. At the very extreme, you have the polar ice caps, which do contain a lot of water ice in addition to frozen carbon dioxide. Plus, you can use mini glaciers in canyon walls and overhangs. But on the other hand, the farther away you are from the equator, the less sunlight you have access to. In 2021, a team of astronomers used orbital mappings of the northern hemisphere Mars to find the best balance between maximizing sunlight and having the easiest access to water. They found that you have to focus on the mid-latitudes, roughly halfway between the equator and the poles, and essentially take the best or worst of both worlds, not getting as much water or as much sunlight as you would prefer. But in the mid-latitudes, you can get some of both, regions that are especially rich in water. There are two regions that the researchers noted. One is the broad, smooth plains of Arcadia, which feature a lot of subsurface ice. The downside of the plains is that you don't have a lot of protection from dust storms. So a better place might be option 2, the glacial networks of Deuteronilus mensae. This region sits at the boundary of a heavily cratered region to the south and a broad, flat plain to the north. There are many grooves and channels carved into this boundary, where water ice glaciers sit year-round, ready for the picking. So that's the best bet between sunlight and water access. But what about radiation? Protection from radiation means you'll need to go underground. The deeper the better. The polar ice caps would be great for this since it would get you both water and protection, but little to no sunlight. Digging your own underground bunkers isn't going to be a good idea, at least for your initial settlement, because we can't assume that you'll have access to decent heavy-duty machinery and mining equipment. The most we've ever drilled into Mars is about 1/3 of a meter with the InSight lander, and then the drill broke. So it's not like we have a lot of experience to go on here. You know what that means. Grab a flashlight, because we're going spelunking. In the early 2000s, a research study called, appropriately enough, Caves of Mars, investigated various possibilities for a good first Martian settlement. Caves offer more than just radiation protection. They might make for easier access to subsurface ice deposits. There might be mineral veins you can reach from underground tunnels. The temperature variations between seasons and between night and day aren't going to be as extreme inside of a tunnel. And you won't have to worry as much about dust storms, although you'll still have to clear off all those solar panels. Unfortunately, Mars doesn't have a lot of caves. You have to rely mostly on lava tubes, which are formed when the external surface of a lava flow cools more quickly than its center, creating a crunchy outside and an empty interior. Some of these lava tubes are completely buried and inaccessible, but some are reachable from the surface, such as one on Pavonis Mons. Now that you've picked the best location with the right balance of water, sunlight, and radiation protection, you've got to start building. But this opens up some pretty nasty questions. Building what? And building with what? There are no trees to chop down to construct temporary structures. There are no campfires you can build to keep warm while you start. There's no wild game to hunt to feed yourself. Mars is dead. Martian settlements will forever be limited by what supplies can be sent from Earth. It's a long, slow, dangerous trip with launch windows open only every 2 years, with each launch costing hundreds of millions of dollars minimum. Any long-term settlement will have to rely entirely on Earth-sent resources or use what is called in situ resource utilization. So we have to be very clever with what we build, where we build, and how we build it. We can probably assume that the first Martian settlers will have some temporary structures available to them. After all, settlements won't begin in earnest until we've already sent many missions to the surface, and we can build off of what those missions leave behind. Shelters, rovers, solar panels, wrenches, stuff. The first settlers won't be completely empty-handed. Plus, they'll have their own descent modules and materials sent in advance. But to really build out a settlement, you need to build, which means you need a lot of raw materials. So much raw materials that we just can't ship it from the Earth. It's too much mass. We need to preserve that precious cargo space for equipment that we can't develop directly on the Martian surface. Things like specialized medicine, advanced robotics, unique cheeses, and contributions to Patreon. That's patreon.com/PMSutter. It's how you can keep this show going. I greatly, genuinely appreciate all of your support. You can also use the link down below. That's patreon.com/PMSutter. In 2006, a researcher named Bruce Mackenzie with the Mars Foundation developed the Homestead Plan, which reasonably approximates the steps a future Mars settlement would have to perform to become self-sustaining, and what they can safely assume and not assume given another few decades of technological development. The plan calls for the use of a hillside base. This way, the people can safely take cover from radiation, but also easily access everything that needs to be exposed to the surface, like solar panels. The plan minimizes drilling and excavation, which is probably going to be a major pain in the neck for quite some time. But the plan does call for some heavy gear to make it to Mars, namely 3 small nuclear reactors to provide a baseline source of power. I know I just said that we shouldn't rely on nuclear power, but here we are anyway. And some miscellaneous mining, refining, and manufacturing equipment. The goal here is to take large amounts of the stuff that's readily available on Mars, like water, carbon dioxide, and Martian dirt, and mix it with small amounts of stuff that we have to import from the Earth, like precious metals. This means that there's a lot of chemistry going on to make oxygen, nitrogen, fuel, and so on. And then there's bricks. Many of the habitat structures will simply dig themselves into the hillside itself, using all those tons of rock to not just protect against radiation, but to maintain the pressure and heat within the modules. But you still have to build a lot of stuff on the outside of the hill, like greenhouses, storage tanks, and the outside parts of the hillside settlement. Mars has a lot of dirt. It does have that going for it. And you can use old-fashioned kilns to turn that dirt, reinforced with something like fiberglass, into bricks. You also need a lot of glass, or something transparent. This is so that your settlers can look outside every once in a while. But it will also be essential for greenhouses. There's no way that we can ship enough food from Earth to sustain a group of settlers for years upon years. They'll have to grow some food locally. And while they will use artificial greenhouses, that will take precious energy to run, potentially straining the power output of either nuclear power plants or solar arrays. So that will have to be supplemented with sunlight greenhouses, which need a lot of glass. Lynn Rothschild, a senior research scientist at NASA Ames, has a better idea. Grow it. Not just the food, although you want to grow that too, but the buildings. She leads a team investigating the use of mycotexture. The idea is that we pack up a frame in a dormant strain of fungus. The fungus is genetically adapted to thrive in the harsh Martian environment. Then we set up the frame and pour some water on the fungus, letting it grow around the frame, creating a sealable, pressurized interior. The team has already been able to grow small structures this way and developed a technique to make fungus-based bricks out of simple ingredients. Practical and delicious. So what do you think? How far away are we from a realistic Mars settlement? Do you think we'll be able to do this in the next generation? What are the biggest obstacles we'll have to overcome? Let me know what you think in the comments. Thank you for watching, and we'll see what the future will bring.